You remember work. Work is when you have a force that's applied over a distance. And you remember a force from Newton's second law is a mass times acceleration. So you need a force to put something in motion. And then while that force is acting over a distance, work is being done. And work is energy. Okay, so there's the basics. Now I'm going to just read the sentence. Work is done when a force moves something in the direction of the force. True. An object has potential energy by virtue of its location, say in a force field. We talked about potential energy like a month ago. For example, doing work by lifting an object increases its gravitational potential energy. And there's a great picture of that. There's this crank pulls on the cord and it raised this object up, 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 up. And now we're going to cut the cord, and the potential energy, it starts to fall and it turns into kinetic energy. Remember all this from the chapter on energy? In an elevated position, the ram, that's the brown colored cube, has gravitational potential energy. When released, the energy is transferred to the pile below. That metal is the pile that you're trying to drive into the ground. Bam, you can see how it got a little bit lower there, right? So this is the classic example of gravitational potential energy being turned into kinetic energy to do some work. It's driving the pile, basically a big nail, deep into the ground. The same idea holds for electric charges. I've got a positive test charge that's attracted to the negative. If it has some potential energy here, and if I cut the string that's holding it, wham, that potential energy turns into kinetic energy. Now this is exactly similar. It's the same story in the picture. We've got potential energy because you had to pull it apart working against the field, and then you let it go and you get kinetic energy. You must understand that point there. If you need to go back a couple minutes and listen to that again, please do, because the next part of the explanation requires that you understand this. All right, moving on to the next slide. A charged object can have potential energy by virtue of its location in an electric field. Work is required to push a charged particle against the electric field of a charged body. So now I've got two positive charges here. I've got a bunch of positive here and a little positive out here. And you can see the hand has got the positive charge, and if it's going to bring it closer, you have to apply a force over a distance, that distance from there to there, from there to there, oops, there to there. And that distance times that force is the work that you have to do. Work is done pushing the charge against the electric field. The work is equal to the energy gained by the charge. So the energy a charge has due to its location in an electric field is called electric potential energy. All right, electrical potential energy. Do you see how that's basically like the gravitational potential energy from last month? Only now, instead of you're working against the gravity field, you're working against the electrical field. You have, in this case, you have to push the positive in against the positive. And once again, if the charge is released, if that person holding it lets it go, it will accelerate, in this case, away from the sphere, and the potential energy, the electrical potential energy will transform into kinetic energy, good old energy of motion. All right, if you're keeping up, great. If not, go back a couple minutes to make sure you got this slide. And here we are at 33.5 electric potential. Here's the good news, it's all downhill from here. So, electric potential is not the same as electrical potential energy. Electric potential is electrical potential energy per charge. I'll get to that definition in a minute. But you'll see it all over the textbook and in places all over physics classrooms. But no one in the real world calls it electric potential. Everyone calls it voltage. That is not the way we talk about electricity, whatever this stuff is up there. Again, this is not how we talk about electricity in the real world. Now, this little equation is true. Electric potential is electrical potential energy per charge. So this potential, what we're going to call voltage, is the potential energy divided by the charge. And what's the potential energy? Remember this situation? That's the potential energy. It's like the gravity situation. The potential energy gets converted to kinetic energy. The potential energy gets converted to kinetic energy, the energy of motion. But I have and potential energy is measured in joules, right? We've talked about joules plenty. More garbage, more garbage. And here we go. That is a picture of Mr. Volta. He looks a little grumpy in that picture. There are a lot of angry old white men in the history of science. The SI unit of measurement for electric potential is the volt. Voltage is measured in volts, and this was all named after Mr. Volta. And here is that same equation. Potential energy is measured in joules, and charge is measured in coulombs. So potential equals potential energy divided by charge. Potential energy is measured in joules, and charge is measured in coulombs. So 1 volt equals 1 joule per coulomb. That you have to know. There will be some homework questions about that. And then from this point forward, for the rest of the school year, 2 weeks of it, we'll talk about volts and we'll talk a little about joules and coulombs. But this is the main point of it. This is where everyday electricity starts, right here. It's called voltage. And the reason that we talk about voltage is because now we can talk about voltages at different locations in an electrical field, and we don't have to worry about those tiny positive test charge. We just talk about the voltage. At this spot, it's 100 volts. At that spot, it's 200 volts. And we don't need to imagine a tiny positive test charge in that spot and figure out what it's going to do. So here we are back at the old balloon on the head. Everybody loves that trick. You probably know that, I've heard that 110 or 120 volts comes out of the wall socket, and that's definitely enough to kill you. But if you rub a balloon on your hair and the balloon becomes negatively charged with all those electrons, how many volts are on there? Yeah, it can be several thousand volts. Now, why is this charge on the balloon not going to kill you? Because there's a millionth of a coulomb. So if I have a millionth of a coulomb and I have a lot of volts, I don't have that much energy. A tiny amount of energy divided by a very, 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 very tiny amount of charge can make a high voltage, but there's not enough energy to kill you. And it's the energy that's the dangerous part. So that's how you can have 5,000 volts on that balloon, and it's not going to hurt you. More stuff we're not going to talk about, more stuff we're not going to talk about, the end. Okay, so the homework questions are very straightforward, and things get easier after this. Thank you very much. Good luck. Have a great day.